All right, hey everybody, I'm Rick from Liquity, and I'm going to talk about the dual oracle design today. So, let me just click on. So I'll just give a brief overview of Liquity if you don't already know about it. So Liquity is a borrowing protocol on Ethereum. Users deposit ETH as collateral, and they borrow our stablecoin LUSD against that. The system needs the ETH USD price at every user operation, or most operations. So particularly when users adjust their loan, and also in redemptions and in liquidations. And the system is immutable and governance-free, so that means we now can't change anything about the code now that we've deployed it. So obviously, immutable systems pose unique oracle challenges. It's like, because we can't change anything about it, we couldn't intervene if anything goes wrong with the oracle we're using. So that means that we can't upgrade the system, we can't change the oracle address or interface. So the big question is, what happens if the oracle fails or freezes or becomes kind of like controlled by a malicious actor? And obviously, just actually go back one slide. So we need some contingency in case that happens, because if Liquity just relies on one oracle, it's in trouble if that oracle goes bad. So the core of the kind of the problem with integrating oracles for us is a knowledge problem. And Liquity, because it's immutable, is in some sense a dumb system. So it doesn't really know anything about the outside world or about the state of oracles in the outside world. It only receives price data from these oracles, and it has to kind of infer something about the states of the oracles based on patterns in that price data, because it can't directly know what's going on with the oracle. Okay, and so we had some design goals with our approach. Basically, we wanted to just optimize for liveness and make sure that Liquity as a system could keep receiving the ETH USD price, as frequently as possible, and have a current and updated ETH price, basically. And so the way we approached it was to have a primary oracle and a fallback oracle. The primary the primary feeds the price to Liquity. If the primary fails, then we switch to the fallback oracle, and the system does its best to transition back to the primary oracle when it comes back online, if it sort of determines that this oracle is trustworthy again. So we considered a few different options for oracles. So just to set the context, it was early 2021. So the landscape was quite sparse. There was a few protocols out there, but actual truly decentralized oracles were hard to come by. And there were projects that were kind of planning to decentralize in future, and they had some kind of, no deadlines, just kind of like some vague promise to actually decentralize, but that kind of wasn't good enough at the time. We considered using a DEX, so particularly Uniswap v2, because we really liked the fact that it was immutable and governance-free, which really kind of fits with Liquity. This was before Uniswap v3 had launched, by the way. So at this time, there was a couple of issues with using Uniswap as a DEX, because you don't have guarantees about the liquidity. So at any point, an LP could pull the liquidity and kind of reduce the resilience of the price and make it kind of like lower the attack cost for that price. And actually, as we saw, most of the liquidity migrated to Uniswap v3 anyway. And also the price on Uniswap is not the best price for an oracle, because it depends what you want, but we wanted the market ETH USD price. And with Uniswap, you get the pair between the ETH and the stablecoin, and that stablecoin price can fluctuate when there's a big market crash or something. So the price can become a bit more inaccurate. So we kind of ruled those out. So the oracles we went with, the primary oracle was Chainlink. It's the largest player in the space. The whole business model is based around kind of maintaining good price data. It's reputation based, and their token value presumably depends on that as well. They have a reasonable kind of level of decentralization of the nodes. They have like different companies in the nodes, and the big caveat with Chainlink is it's a multi-sig admin basically. So they have complete upgrade control over their smart contracts, And there's been like quite a lot of discussion around that recently. I'm sure you've probably, probably seen that online. And our fallback oracle is Telor. And we really like Telor because it's like fully decentralized, as Nick's been talking about. It incentivizes honest reporting, proof of stake. And yeah, upgrades are voted on by token governance, and that really fits with Liquity's values. So yeah, Telor is a fallback. I think when we were like building our system, Telor had just launched the version that we were going to use, like just a few weeks before our launch. So it was at that point less proven, but now it's clearly like, yeah, it's stood the test of time since then. So one thing, another important piece was having static endpoints. So because Liquity is immutable, we can't change the address or interface of the contracts, and we need oracles that are going to have constant addresses and like have a proxy contract that we connect to, and then if they want to upgrade, they can sort of swap the logic out under the hood. And so yeah, both Chainlink and Telor had that, and that was ideal for us. So why didn't we take an average price of like kind of multiple oracles? Well, like if you take a mean, it's kind of useless, because if one oracle is dishonest or giving bad data, then the mean is corrupted. If you take a simple median, then if somebody controls, say, the weakest oracle, they can insert themselves into the middle and become kind of the source of the price for our system. It's kind of a bounded attack because they can only insert themselves between the two honest oracles. But if they say controlled two of the weakest oracles, the two weakest oracles, they could then choose any price they wanted. So yeah, we ruled out a mean or a median as well. And yeah, we went with this fallback approach. So just to cover some of the security pieces, obviously auditors probably hate the look of this function because it's a bunch of nested if statements inside the fetch price function, and it's has a lot of different branches to it. But that's kind of the trade-off we had to make with designing this kind of system. The increased code complexity, it increases the surface area where bugs could slip in. And yeah, in principle, the system is more resilient, but that's if it's kind of like working perfectly as intended. So in practice, there's this much higher security burden on the developers to get it right and like make sure it it does what you want it to do. There is one security benefit of the fallback design, I will say, is that most of the time when the system is like using the primary, it's really not even reaching or executing most of that code. So actually, like most of that price feed contract has never been touched yet, and hopefully it won't be, but it's there if we need it. Okay, so just a quick overview of our Oracle logic in Liquity. The system calls both oracles when it needs the ETH price, so every user operation, like whenever the loan is adjusted, basically. We keep track of the state of each oracle, whether they're frozen or broken or live. We prefer the primary oracle, but we switch to the fallback if we need to. If both oracles are frozen or broken, or just kind of untrusted from some previous, breaking previously, we use the last good price the system has seen. And if the primary does fail, the system will do its best to actually transfer back to using the primary when it's confident that the primary is really live and providing honest data again. Okay, so the criteria for a frozen oracle, basically it's if an oracle is giving Liquity good data, but it's just out of date. So if the timestamp is more than 4 hours old, we consider the oracle frozen. And if the primary is frozen, it will switch to the secondary. So why do we choose 4 hours? Well, it's not like rocket science, honestly. It's like, we sort of thought it's our best guess at a sweet spot because it should be long enough to avoid false positives if, say, there's like very low ether volatility and the primary oracle price doesn't update. So Chainlink have a minimum update of 3 hours. So we wanted it to be longer than that. But we also wanted it not to be too long, because if it's too long, then if Liquity doesn't see a current ether price for very long, it could actually get into a very unhealthy state and become under-collateralized. So 4 hours was kind of our best guess at that sweet spot there. And yeah, this is just the Chainlink update frequency that we based our kind of analysis on up to early 2021. And you can see like 2 big spikes where it went above 4 hours. And had Liquity been live at that time, that's kind of when we would have wanted to switch from the primary to the fallback oracle. Yeah, we launched sort of after all this data, in 2021. But yeah, all credit to Chainlink. The update frequency has only improved since then. I think they integrated like off-chain signature aggregation, so it kind of they can avoid any network congestion issues now that might cause a really long delay. So when do we consider an oracle broken? Basically, if it's just returning like bad data or weird data. If it's like the timestamp is like in the future, or it's like a negative price, or it's just not responding properly. And yeah, if the primary is broken, it switches to the fallback. So yeah, just a couple of technical details. As I said, every operation calls this fetch price function. It fetches 3 prices: the current price from the primary, previous price, and the current price from the fallback oracle. Yeah, there's no reverts in this function because we don't want the top-level user transaction to revert. So even if kind of the oracle's gone bad, we don't want we still want the user to be able to adjust their loan and based on the best price that we can see in the system. So we use like try-catch statements for all the external oracle calls. The gas cost of all this oracle fetching is around 60K, which is not terrible, but it's like it is a cost borne by the users at every action, so they do feel it and they pay for it. Okay, so this is the Liquity Oracle Logic state machine. So this is like the state that the Oracle component of Liquity, the states that it can go through. So it starts off in state 1 using the primary. If something bad happens, it freezes or breaks, then Liquity will switch to using the fallback oracle. And you can see state 3 here is like a state where both oracles are untrusted, so they've probably both broken. And in that case, we just use the last good price that we've seen. And we continue using that until we have like good evidence that we can return to the primary. And you can see also each state does its best to get back to using the primary oracle. All right, and yeah, this is how we switch to the fallback oracle. If the primary is broken or frozen, we switch. And also, if there's a deviation between 2 consecutive primary price updates that's greater than 50%, so if there's just a really sudden big ETH price jump or ETH price crash that just seems too big, bigger than 50%, then we will switch. But we'll only switch if the secondary oracle doesn't agree. Because if it does agree, then we'd probably infer that like actually that's a legit market movement. So yeah, we want to make sure that there's actually a discrepancy there before we switch to the fallback oracle. Because if there's a big discrepancy, we can infer that okay, something's gone wrong with the primary. And okay, so one final question is how do we switch back to the primary oracle? It's an epistemic issue, so it's like a knowledge issue. Again, how can we really be sure that this price data we're seeing is honest, is actually the real market ETH price? The oracle may have broken and come back online again, but what if a malicious actor has control of it and is just feeding us bad data? So it's not easy to solve. It's difficult. The way we do it is we say we'll switch back if both oracles are live and in sync. So if the price is within 5%, and we're kind of inferring that if that's the case, then it's more likely that that's really the market price than it is that both oracles have been compromised. And that's not a perfect assumption, but it's it's probabilistic. Okay, so in summary, yeah, that's the fallback oracle design. It's mostly useful for resilience to technical failures or griefing attacks where the oracle kind of goes offline or freezes. It's not great for resilience to price manipulation because it's always possible for an attacker to kind of fly under the radar and change the price. If they have control of the oracle, they could just change the price in a way that is within the boundaries of whatever detection kind of limits you've set. And so yeah, it's really it's just tricky to defend against that. the big trade-off with this whole design is the more fallback logic equals more code complexity, higher gas costs, and we think like the complexity of the code should be kind of proportionally matched with security work. So you need to put in the time and effort and resources on security. We did a full audit just for the Oracle components, and a ton of testing and fuzz testing and unit testing on that piece. So that's it, and I guess everything moves quickly in blockchain. So if anybody is building any kind of like multiple Oracle system or dual Oracle system, that would be great to talk about. And if anybody has any questions, of course.